Hello and welcome to the first video on modular forms. As you may know, additive number theory is concerned with the question of writing an integer as sum of integers from a certain set. For example, it asks the question of in how many possible ways you can write an integer n as a sum of positive integers. And this gives rise to what's so-called a partition function. It also asks the question of the possibility or the number of ways you can write a number, a sum of numbers from any set. Like it can be the set of squares of numbers, the set of cubes, and this question can get really hard. It turns out that when studying modular forms, relations that are far from being obvious are like just natural consequences of working with certain modular forms. So in this course, we aim at constructing some modular forms and studying their properties. To be able to construct our first example of a modular form, we shall start with a short discussion on elliptic functions. So we're going to start by defining what elliptic functions are and give some of their properties, and then we're going to transition to our construction of modular forms. So this first lecture is about elliptic functions. So what is an elliptic function? Here's the definition. An elliptic function f it's a meromorphic function and it's doubly periodic. So let's pause here and just talk about these terms. So by meromorphic function, I remind you that it's a function that is holomorphic up to some discrete set of poles. And you can think of it as, you can think that f of z takes the form p of z over q of z, where p and q are holomorphic, and it has finitely many poles in compact subsets of the plane. And it has equal number of zeros and poles. So these are the essential things we would need about a meromorphic function. These are more of properties of meromorphic functions, but these are the things we'll be needing for this course. A doubly periodic function, it's a function, so f has two periods, omega 1 and omega 2, and by that I mean, if you look at f of z plus omega 1, this should be equal to f of z, and same if you look at f of z plus omega 2. Okay, so why are we introducing elliptic functions? So it turns out that one of the elliptic functions we're gonna construct has, like, if you expand it in a Laurent expansion, it turns out that its coefficients will be actually modular forms of even weights. We're gonna come to that. However, to reach that, we would need to start by constructing some elliptic function that is nice and would give rise to a modular form. However, before we go on and start our construction of elliptic functions, I should perhaps give you the definition of modular forms. So, a modular form of weight k, or perhaps an entire modular form of weight k, is a holomorphic function that satisfies three properties. It's a holomorphic function that is defined on the upper half plane. So it's defined on all the complex numbers that have a positive real part. And second, it satisfies the homogeneous equation a tau plus b over c tau plus d is equal to c tau plus d to the k f of tau, where a, b, c, d is a matrix that is that has integer coefficients, and its determinant is +1. And furthermore, we require f to have a Fourier expansion as such and don't worry much about this for now. We're gonna come back to this definition later, but for now I wanted just to present the definition for you because it's the main thing we'll be talking about later. So back to elliptic functions and the construction of an elliptic function. So to be able to construct a first example of an elliptic function, we will need to study some of its properties. So here's a definition. I should perhaps also I should perhaps say that for the doubly periodic function, we require that the ratio of the two periods is not real, because it turns out if they're linearly dependent over R, we're gonna just be getting trivial examples of elliptic functions. So we restrict ourselves to linear independent periods for the doubly periodic function. And here's the first definition. We define the lattice. We define the lattice generated by omega 1 and omega 2 with the notation omega, big omega at omega 1, omega 2 to be the set of periods m omega 1 plus n omega 2 such that m and n are integers. So in other words, what we're doing here is that we have this kind of picture where say this is 0, this is omega 1, and this is omega 2, and we collect all these integer linear combinations of these two periods, and I call these periods because as you see, if omega 1 and omega 2 are periods then of a certain function f, then by induction it's clear that an integer linear combination of these is also a period. Okay, so the reason I'm introducing the definition of a lattice is that it turns out that an elliptic function is completely determined by its values on a parallelogram given by this, because remember it's a periodic function, right? And we call this parallelogram a period parallelogram. And as you can see, if we're taking omega 1 and omega 2 to be linearly independent over R, like this lattice is gonna cover the whole complex plane, right? So we're gonna now start by studying properties of elliptic functions. So here are some properties. So here's the first theorem. An elliptic function f, say, with no poles is a constant. And let us prove this. It's just a one-line proof. Remember, an elliptic function is a meromorphic function, like it has a discrete set of poles. Now, if we say that it has no poles, i.e. it's holomorphic, it's entire, then since it's periodic, then its values in the whole complex plane is determined by its values in this parallelogram, which is a compact set. Now, a holomorphic function is continuous, hence this f is bounded on the parallelogram, which is compact, right? And since it's bounded on the parallelogram, it's bounded everywhere because it's periodic, right? Like its value on the parallelogram determines its value everywhere else, and hence f is bounded, and it's entire. So by Liouville's theorem, it's constant. And this completes the proof. Now, interesting enough, just as we said, we have a symmetric theorem, which is an elliptic function with no zeros, let's call it f, with no zeros is also a constant. Like, we're trying to eliminate the trivial cases so that we construct our first non-trivial example of an elliptic function. Since we're using this property of a meromorphic function from complex analysis, that a meromorphic function has equal number of zeros or poles, and poles, it follows that if it has no zeros, thus it has no poles, and thus it's a constant by theorem 1, right? So this is, the proof is just theorem 1. Okay, so there are further properties that we're gonna need, and this is theorem 3. Theorem 3 is gonna have a nice corollary, which is a nice property about elliptic functions, and this is in fact the last property that we need of an elliptic function. So theorem 3 will say that given an elliptic function, say f, the contour integral of f over the boundaries of the parallelogram, the period parallelogram, let's call this P. So if we run over the boundaries of P, if we consider this path, right, is in fact equal to 0. And this is also an easy theorem, and here's a quick proof. Well, the function is doubly periodic, so therefore it's also totally determined by its values in the parallelogram, period parallelogram. So this is 0, omega 1, omega 2. And if we're integrating over this path, now just so that the statement of the theorem makes sense, let me just mention that integral is indeed well defined. I mean, that we can assume that the integral is well defined without loss on generality, because if we had a pole, say on some edge, we can either translate this parallelogram, say this is a parallelogram P, we can translate it to some Z0 plus P with having no poles on the edges, or we can do something like we can go over this pole as such, and then our statement will be okay. And now that we fixed this, the proof is just one line again. Well, f is periodic, right? So its values on this line matches its values on this line, and similarly its values on this line matches its values over here. Thus the integral over opposite paths will cancel. So just to clarify, this is gonna be the integral over f is equal to the integral, let's call this gamma 1, gamma 2, gamma 3, gamma 4, and the integral over the boundary of parallelogram will be just be the sum over the gammas, right? I equals 1 to 4 of f. And we said that the integral over gamma 2 cancels the integral over gamma 4, and the integral over gamma 1 cancels the integral over gamma 3, and this will be 0. Okay, so why are we saying this? Well, we're saying this because remember, from complex analysis, the integral over a closed contour, it has to do with the sum of residues within that contour. And this will allow us to understand an additional property of elliptic function. So, so here's theorem 4, or let me call it corollary to theorem 3, and it just says that the sum of residues of an elliptic function is 0. And why is that? Again, the proof is one line. Well, if the integral over the boundary of the parallelogram is 0, it follows by residue calculus that the sum of the residues of f in the parallelogram is 1 over 2 pi I, the integral over that boundary of f. And we're again assuming that the boundary has no poles, because again we can either translate it or go around the poles because these are finitely many poles. Remember, a meromorphic function has finitely many poles inside any compact set of the plane, and this was just proven by theorem 3 to be 0. Okay, so there is enough of properties because this gives a pretty good classification, and we're gonna start by constructing our first example of an elliptic function. But before that, let's note that corollary 3 implies that we should have at least 2 simple poles or a double pole inside the period parallelogram. Okay, and why is that? Because it can't have just one simple pole, because the residue won't be 0 in that case. So it needs to have 2 simple poles that cancel each other's, or a double pole in each parallelogram. Okay, and now we turn to the construction of the first elliptic function. Okay. So this idea is due to Weierstrass. So since we should have a double pole or at least 2 simple poles, you might think of like kind of looking at terms of the form z minus omega, where omega is a period, and then we run over all the periods. If we sum over all the periods in the lattice, now I should stress here that having a pole in the period parallelogram, in this period parallelogram, it necessitates the existence of a pole in every period parallelogram, because by periodicity the values of f here are equal to the values of f here. So if it has a pole within this parallelogram, it has a pole in every parallelogram, and thus the function we should construct should satisfy this. So what we're gonna do is that we're gonna try to construct a function that has a pole at inside every parallelogram. So this is one way of doing that. We take a double pole at every period, and hence we're guaranteed that we have a function with poles in every parallelogram. However, this is problematic. Like, we have some problems here. The first problem, it's not absolutely convergent. And why would we need that? Well, because when we want to prove periodicity of the function, when we want to prove that this function is periodic, like this is the function f of z, when we want to prove that f of z plus omega 1 is equal to f of z, we're going to be summing 1 over z minus omega plus omega 1 squared, and we're going to be running over all the periods in the lattice. We're going to need to use the argument that as omega runs over all the lattice, omega minus omega 1 is going to run over all the lattice, right? However, these are two ways of summing this series, and since we need the sum to be independent of the rearrangement of the sum, we need some sort of absolute convergence of the series, which we don't have here. And I don't think I need to talk about anything else. So the main problem here is that it's not absolutely convergent. And just to be clear here, when we're talking about a lattice, like we're fixing two periods, omega 1, omega 2, that are linearly independent over R, and we're considering the lattice generated by these, just as we defined before. The lemma says that given the lattice big omega of omega 1, omega 2, and these are being linearly independent over R, the sum of 1 over omega to the alpha, as omega ranges over all the periods that are non-zero. If we consider this series, this converges absolutely if and only if alpha is strictly bigger than 2. Here's the proof of the lemma. So it's more of a proof by a picture. So here's what we're gonna do. So let us look at the lattice again. And say this is 0, this is omega 1, and this is omega 2. And what we're gonna do is that we're gonna consider the annulus, and by that I mean, let's consider a circle here, and we consider a bigger circle. Okay, it doesn't look pretty much like a circle, but you get the idea. So we consider two circles, say of radius n and of radius n plus 1. And we ask the question, how many periods are in between these two circles? And we're gonna count these. right? The reason we're gonna do that is that we wanna find a partial sum that is easy to analyze with respect to alpha. So here's the idea. Let us denote, let k of n, say, be the number of periods inside the circle Cn, and let's call this circle Cn, meaning the circle of radius n. And for simplicity, let us assume that these parallelograms are in fact unit squares. Let us assume this, since the argument for a general parallelogram can be just motivated by some sort of scaling argument. And we ask the question, how many parms, in this case unit squares, can we fit inside a circle? Well, let us consider a special circle here. Let's consider the circle Cn minus 2, okay? So if you consider this circle, now this circle has an area pi n minus 2 squared, and that is unit squared. Well, what does that mean? Well, this means if we have this circle and we keep covering it by these unit squares, if we consider all of these unit squares and we move a bit, so this is n minus 2, and if we move a bit to the circle of radius n, this circle is gonna contain all of these unit squares. And each of these unit squares actually have 4 vertices, right? They have 4 vertices, and thus 4 times that many unit squares actually fall inside the circle of radius n. And by that I mean the number of periods, which are the vertices of the squares, falling inside a circle of radius n is at least that many. 4 times that many squares. I hope this is clear. And by a symmetric argument, we can show that the number of periods that are inside a circle of radius n plus 1 will lose to 4 times the area of that circle, because these are the unit squares covering the circle, and each of these have 4 vertices, so it's going to be losing to that many number. And this is all to say now that k of n plus 1 minus k of n plus 1 counts the number of periods in the circle of radius n plus 1, and this counts the number of zeros in a circle of radius n. And remember, this is what we wanted to count. We wanted to count the number of between these two circles, and that number is literally this difference, right? And this, by these two inequalities, will lose to 4 pi times n plus 1 squared minus n minus 2 squared. And you can simplify this. It's gonna be some constant times n. Okay, so why did we do all of that? We did all of that because we want to introduce the partial sum now. That is the sum over n equals 1, 2, and so on up to n of all of those periods in each analysis. So here this partial sum is running over the analysis, like this is the place in between the two circles. So how many of these omegas are we summing? Well, we're summing that many. So it's gonna be k of n plus 1 minus k over n. And it's not so hard to see that this will also be lower bounded by constant times n. And this is all to say that this partial sum will be bounded between two things, and this will be of the form something like c n over n alpha, because if you take alpha here you have this, and from the lower side you're gonna have the sum of some c prime n over n alpha. And this is all to say that, well, this is convergent if alpha is strictly bigger than 2, because it's the sum of 1 over n to the alpha minus 1, and you need this to be strictly bigger than 1. And this will diverge if alpha is less than or equal to 2. This is all to say that this partial sum, which you can easily see that any other partial sum falls in between two of these partial sums, is actually convergent if and only if alpha is strictly bigger than 2. And this is all we needed to show that the statement of the lemma, if we sum over the periods in the lattice in absolute value, we get convergence if and only if alpha is strictly bigger than 2. And as a corollary to the lemma that we just proved, we're going to prove that if alpha is strictly bigger than 2 and r is positive, then the series, the sum over 1 over z minus omega to the alpha, if we sum over all the omegas on the lattice that are strictly bigger than this given positive number, let's call this f of z, converge absolutely uniformly on the disk z less than or equal to r. Like for every z less than or equal to r, this is an absolutely uniformly convergent series. Remember, the function should have poles, right? But we're trying to construct an elliptic function here. So the function should have poles. So we can't guarantee, so we can't get convergence everywhere. Like we can't get convergence of this sum everywhere, because it's gonna blow up somewhere, right? Because it has poles. What we can prove, however, is the tail of it is absolutely uniformly convergent, so that rearrangement is okay. And once we prove that, here's a remark. If we prove this theorem, which is an easy thing to prove now that we have the lemma, we have a series that is locally absolutely uniformly convergent. If we consider the function g of z given by the sum over omega less than or equal to r of 1 over z minus omega to the alpha, z minus omega to the 3, for example, plus the sum of omegas strictly bigger than r, 1 over z minus omega cubed. So if we pick a particular alpha that is strictly bigger than 2, we have an elliptic function, because this is an absolutely, it's a locally absolutely uniformly convergent series, so rearrangement is okay, so periodicity is okay of the function, and it's meromorphic because this is an absolutely convergent series on the disk z less than or equal to r, and this just has finitely many poles of order 3, and thus the function is meromorphic. So it's enough to prove the theorem, and you can plug your favorite alpha that is strictly bigger than 2 and get an elliptic function. So let's prove the theorem real quick. So the theorem, so the proof goes as follows. So we want to apply a Weierstrass M test. We're gonna bound this thing to the alpha, we want to bound it by some m over omega to the alpha, because if we could do that, we can use the lemma that we've just proven here. We have absolute convergence, and the sum would converge absolutely uniformly by Weierstrass M test. So this is what we want, and to achieve this, we assume that z is less than or equal to r, because we're trying to prove absolute convergence on the disk. And we assume omega is strictly bigger than r, because this is the sum that we're interested in. And we study this term. So let's look at this inequality. This is what we hope for. So if we do if we bring this here, the inequality that we're looking for is something like this thing is less than some constant, right, m prime. Now also finding such a constant is equivalent to finding some constant where z minus omega over omega is bigger than or equal some m double prime. So it's enough to find some constant m double prime where this inequality is true. So to find that constant, that is an easy thing. If we look at this thing over here, this is gonna be in absolute value, it's gonna be 1 coming from here minus z over omega if we change the sign in the absolute value, and this will be bigger than or equal 1 minus z over omega by triangular inequality. And this thing, well, z is gonna be less than r, and omega is strictly bigger than r. And since all of our omegas are strictly bigger than r, we may pick the omega naught, the omega with the smallest modulus above r. So we may pick the omega with modulus being some r plus d, where d is some positive number, such that all of these periods that are with modulus strictly bigger than r are like they have modulus strictly bigger than omega naught. And recall, this is possible because in every compact set a meromorphic function has finitely many zeros. So once we've done that, it follows immediately by this inequality and this thing, and this inequality, that this thing is bigger than or equal 1 minus r over r plus d. And this is the m double prime we're looking for. And this completes the proof of the theorem, and this completes the video.